Okay, so let's go ahead and get towards the equations of motion by adding this rotational effect. Here we are again looking at du dt. Obviously, we are heading towards F equals ma again in the rotating framework. So that we said when we do these cross products, we get du rotational dt in the rotational framework plus 2 omega u rotational plus omega cross r. That looks like our favorite Coriolis, and this is the centrifugal force. Okay, so every time you have rotation, you're going to have the rotational effect and the centrifugal force. So the inertial framework we used before without any rotation, the equations looked like this. Du dt plus 1 over rho grad p plus gz equals F, the friction force. We had left this just as is, which we will continue to do for now. And let's look at this equation now by adding our Coriolis acceleration and centrifugal acceleration. Centrifugal force, right? Du dt plus 1 over rho grad p plus gz minus 2 omega cross u minus omega cross r plus f. We just took things on the other side. So we are now in the rotational framework. We are just going to stop carrying the inertial and rotational separately and just stick to rotational framework with the rotational terms in them. Okay, so du dt and u here refer to the rotational framework, so we dropped the subscripts completely, because from now on we are always in the rotating framework. Forget about the inertial framework. Okay, so minus 2 omega cross u, if you know how the cross products work, here is u and here is minus 2 omega cross u. So when the rotation is counterclockwise, like the Earth from the North Pole going west to east, the deviation because of the rotational effect is to the right of the direction of motion. To the right of the direction of motion. I have a podcast on this on YouTube. You can go and check it out with the animation and so on as to how this comes about. But nonetheless, here, just remember this. Minus 2 omega cross u is going to be to the right. Obviously, if you change the rotation direction as in the southern hemisphere, it's going to flip, right? This is something we will come back to later on when you are in the same direction as the rotation of the body you are on. It's called cyclonic, but we'll come back to that. So minus omega cross r can be written as a gradient of a potential. So this can be written as gradient of omega squared r squared over 2. These kind of vector calculus are in the appendix of the book that I'm not going to go into, but you should go through them to make sure, unless you already know how to do this. I think you can take ijk and write omega r and then do the whole thing. What is a potential? It's the same sense as we used in potential energy. It's a ability to do work, right? So centrifugal acceleration can be written as a potential, and obviously we can also do the same with gravity. Gravity is essentially like potential work, right? So remember the ball on the hill, if we pushed it, it went down because of gravity. So gravity also can be written as a potential. I think you know where we're going with that. So we can combine these and we will get our old familiar modified gravity or measured gravity. So we will define phi, the gravitational potential, as gz minus omega squared r squared over 2, which we can combine and write as grad phi. So we took omega cross r from this side and combined with g to produce this modified gravitational potential, or measured gravity as we called it before. Okay, so du dt plus 1 over grad p plus grad phi equals minus 2 omega cross u plus f. So two things changed. This looks a little different than the non-rotational framework we had done before, and this additional term, which is the rotational effect, has been added. Very simple, very straightforward. So to see the analogy, we defined the relative height of the water column in the rotating tank using that reference parabolic surface, which we will come back to. And the expression we derived will look exactly like this equation with the full rotational effect. So we'll look at that in the next podcast. But make sure you understood how we added the rotational effect by writing u rotational plus omega cross r, doing du dt, and then going back to our F equals ma equation. That's all we have done, and the additional information you got now is that when the rotation is counterclockwise, the Coriolis effect or the rotational effect is going to deviate the fluid parcel to the right of its direction of motion. So it doesn't accelerate, it changes direction. So some people insist that hence it should be called an apparent force. It's not a real force, but obviously we'll drop all that and just start saying Coriolis force, especially when we get into geostrophy and so on. Okay, I'm splitting this randomly into little pieces, but I hope you can follow with the book and with the podcasts how the derivatives, how the derivations are done.